So the topic of our presentation is auditory scene analysis, or rather a month-long dive into struggle with this topic that some people helped us with, and we're grateful. To understand the significance of this topic, you have to think about how all the sound in your auditory environment comes to your cochlea as a single mixed wave, and yet somehow your brain is able to segregate this mixture into auditory perceptual objects you perceive as coming from different sources and locations. How is your brain then able to do this? And are there computational solutions that approximate human-like performance? In what follows, we will first give you a brief introduction to cognitive problem, and then followed by one of the computational implementations of it, but we'll only have time for one of the implementations due to the constraints.
So let's dive into the cognitive theory first. So Bregman was one of the first to give a very comprehensive theory of auditory scene analysis, and he proposed that this occurs in two stages: decomposition, which involves breaking down the auditory input into its elements, and then grouping, in which these auditory elements are grouped together into a stream using mechanisms which group sources according to statistical regularities of the sound, like common offset and onset, interaural time difference, periodicity, etc. There are two major grouping mechanisms: simultaneous and sequential. Simultaneous grouping cues involve grouping elements across frequencies, whereas sequential grouping cues are grouped across time. And the decomposition aspect of the peripheral auditory system, the first part is quite well studied. However, the neural correlates of grouping require more exploration. So one way that we can study these statistical regularities on how we group the group sounds together using the computer is through independent component analysis, which I'll now hand over the mic to Nadia.
Okay. So to drastically change course, let us think about independent component analysis, which was developed as a solution to the blind source separation problem. The way ICA approaches this task of separating sound is by looking for independent components in a data set. We can model the incoming mixture of sound as a linear combination of the source signals and the mixing coefficients alpha. We can also present the model in a vector matrix notation here, where matrix A is the mixing matrix and vector S is a vector of source variables. And our goal is then to find a demixing matrix W, which is the inverse of the mixing matrix A. So to put it briefly, if we assume that a matrix A has transformed our original data, we want to find the inverse of this transformation to get a scalar approximation of the original sources. ICA operates under two assumptions. First, it assumes that the source signals have a non-Gaussian distribution. To demonstrate why non-Gaussianity is important, look at the Gaussian distribution on the left as opposed to the non-Gaussian distribution on the right. You can see that the density is completely symmetrical and circular, therefore it does not contain any information about the directions of the mixing matrix. We can arbitrarily put these directions anywhere. The second assumption that ICA makes is that the source signals are independent of each other, which is usually a reasonable assumption to make if sound is coming from different sources in the environment. So to put it in non-rigorous terms, ICA involves projection pursuit, or the pursuit of interesting projections in a multidimensional data set. To see how ICA is able to find these projections, we can look at the two main principles that it operates under: maximization of non-Gaussianity and minimization of mutual information. If we make cellular transformations, we can express Y, which is here the estimate of one of the sources, as a linear combination of all of the sources that we have in this data set. Then if we go back to the central limit theorem, we know that a sum of random variables, the distribution of a sum of random variables is always more Gaussian than the distribution of the variables themselves. Therefore, Y, which is a linear combination of several of these independent components, will be more Gaussian than the components themselves unless it is equal to one of the components. So this is the assumption, this is the derivation that we make and come to the idea that if we maximize the non-Gaussianity of W transpose X, we will get one of the independent components. Another way to approach ICA is through an information theory-based approach, which tries to minimize mutual information between the estimated sources. Well, we'll now have to look at what mutual information is. Mutual information is a measure of dependence among variables. So a dependence structure among variables, or a copula. For the purposes of understanding this code, we can now see here that the mutual information denoted by I is visualized or expressed in terms of entropy. And for purposes of understanding this equation, we can think of entropy as code length, or the space we need to store information. Let's say we have two variables, or the two sources in our case, and we want to store these variables. If these variables are informative about each other, we can store them together to minimize the space needed for storage. However, if the variables are independent, therefore are not informative about each other, the space required to store them together is not much larger. To store them separately is not much larger than that required to store them together. Then we can say that the mutual information is minimal when the space required to code the variables separately is the same as the one required to code them together. Therefore, they're maximally non-informative about each other, or they're maximally independent of each other. Then, in this case, we can conceptualize ICA as a pursuit of a demixing matrix that minimizes the mutual information of the estimated sources. And now, having looked at the principles of ICA, we can take a look at the code, which is more of a proof of principle demonstration than a state-of-the-art ICA. We took the ICA algorithm from GitHub, from this person, and then we extrapolated from there and added some of our own things. I'm going to now play a mixture of sound. It's probably going to be a bit loud, but bear with me for a second.
The guardians of the electronic stock market, NASDAQ, who have been burned by past ethics questions are moving.
This is the mixture that we used. We took this mixture twice because we assumed that we have two microphones. And what we want to do with this code is we want to separate these mixtures using ICA. And we want to see how well this works. So what we do after that is we use one of the implementations of ICA, which in this case is Phoebe. It's one of the oldest implementations. I think it's actually the oldest one from 1989. It's definitely not state of the art, but it is quite easy to implement and also to visualize. Then what we do is we graph the generated signals as opposed to the original signals, and we look at how it's able to separate them. So these are the generated signals in the form of in a waveform. These are the original signals, and you can see that they look quite similar to one another, but we can go a bit farther and look at them as spectrograms. This would be a mix, the spectrogram of a mix, and these would be the outputs. And here you can probably guess that this is a siren because of the way it changes over frequency and time, and this would be somebody speaking, and we can see that the original signals are identical to the outputs that we get through ICA. And we can say that in this case, ICA was quite successful, except for some indeterminacies here that you've probably noticed, and Radhika will talk a bit more about now.
So as Nadia already mentioned, ICA is not without its limitations. So for computational limitations, ICA does not account for the sign and the scale of the sources it gives. And it cannot also determine the output order of the sources it gives. So we can see in the code that Nadia is showing right now that generated signal 1 is not the same as output signal, is not the same as original rather than the original signal 2. And original signal 1 and generated signal 2 are the ones which are same. And we can also observe, if we see in generated signal 1 and original signal 2, that their signs are inversed. So this is what was the computational limitation. There's also biological limitations in terms of the fact that ICA is not a very biologically plausible model. So the way the human cognition works is that we do figure ground segregation. So what the signal we want is the figure, whereas everything else is the background. But ICA aims to separate every single source signal. And further, it has untenable assumptions, such as the number of microphones, which in ICA should be as many as there are source sounds, which is not always possible in the human auditory system. And also that the microphone should be stationary, which is also not always possible since humans can also perform auditory segregation during movement. There are more biologically plausible models, and we did go into them. The computational auditory scene analysis, also known as CASA, is a very interesting model. However, we do not have time to go into it. But if you have any questions, we would love to answer them the best we can. And so finally, to conclude our 1 month of research, or as we put our dive and struggle and attempt, is that IC is great if the assumptions hold true, as we saw in the code. However, it is not a very good biological model. So for better biological modeling, we go into CASA, which you can ask us about. Thank you.
Well, I mean, with this, with you prepared your question perfectly, yeah. So like, it's now I want to know what is SCASA? What how does it relate to ICA? It's impossible not to ask that question. Nicely done.
Oh, is that an actual question?
Yeah, that's an actual question because you prepared it for yourself.
Yeah, well, because the whole idea for us was to find a thing that models human like audition. We first went to ICA because it is very widely used as a solution to the cocktail party problem and sound segregation. But then in the middle of it, we realized, oh, wait, it's not really a very biological model. And then let's see what else is out there. And we encountered this more of a direction of research into computational auditory scene analysis, where the models use the models use a model of the peripheral system. So they use a model of the cochlea, most of them, as well as some of the higher order processing functions. And what differentiates ICA from CASA is that CASA highlights the middle processing. So it first separates the sound into frequencies, just as cochlea would, and then applies statistics onto that separation, if that makes sense.
Yeah, it was a bit packed. So it makes the analysis more related to the composition at the intermediate sensory level. So basically, what makes it more plausible is that it uses plausible frequency decompositions.
Yes, it involves the model of cochlea, which makes it more plausible because that's how our brain gets the information.
And is the mechanism similar to ICA?
Well, it looks. Oh, go ahead.
Yeah, I was going to say we tried to get into the code of this, but it was a little difficult to get into that. So the way we understood it.
But is it the composition matrix? Is it the same thing that you had before? Like, because what I mentioned in the chat was that it's ICA is a lovely linear model that takes the samples in time t to decompose. So it basically takes the frequencies away at any given time,
yeah.
which is fun.
Yeah.
And the question is this the same as in CASA?
No, what CASA does is it does correlations. So either autocorrelations or cross correlations, depending on what kind of information it wants to get from the data. For example, if we want to get interaural time difference information, which I don't know if everyone understands what it is, but the sound comes from different years, and sometimes there's the sound will come faster to one year than the other. And then what we do with cross correlations is we want to correlate the information coming from different years to see what the delay between them is. And that's what CAPSA does.
Got it. I think we had a it was a stream. So thank you very much. Go and vote. And let's go for the next one. So that's Tim and Martijn.